Our next topic in haloalkanes and haloarenes is reaction with metals. We have covered up nucleophilic substitution reactions and elimination reactions. Now next reactions are reaction with metals. So we are doing the reaction with magnesium metal here and with sodium metal. So first is with magnesium metal. So when haloalkanes like Rx reacts with magnesium metal, reaction takes place in presence of dry ether and we get RMgX, which is a Grignard's reagent. RMgX is a Grignard's reagent. Now one particular example I am taking. R we are taking is CH3CH2Br, that is bromoethane, and to this when we add magnesium metal in presence of dry ether we get CH3CH2 and here Mg will come, MgBr. This is called ethyl magnesium bromide. This Grignard reagent will form. Now important thing is Grignard reagent, they are highly reactive. Grignard reagents are highly reactive compounds and they can react with any source of proton which has proton, like water has proton H plus in it, and convert the Grignard reagent alkane. Convert Grignard reagent to an alkane. So if to Grignard reagent water is added or it comes in contact with water, it will take this H plus from water and this becomes RH. RH is the general formula for alkane. So alkane will form and what is left is MgOHX. MgOHX. Example, if R is CH3CH2MgBr, ethyl magnesium bromide, when comes in contact with water, this becomes CH3CH3, that is ethane, and plus we are getting MgOH and Br. Both OH and Br, they link to the magnesium metal here. So we are getting an alkane if Grignard reagent prepared comes in contact with the water. So if we want Grignard reagent to be like this only, then we have to do the reaction in presence of dry ether. Now after doing the reaction with magnesium metal, next we are doing is a reaction with sodium metal. Reaction with sodium metal, and this reaction we have already done in 11th class, which is called Wood's reaction. In Wood's reaction, haloalkane is reacted with the sodium metal. Haloalkane is reacted with the sodium metal in presence of dry ether. Two molecules of haloalkane, they react and we get alkane along with NaX. Now to understand this reaction, I am taking two molecules of haloalkane and writing these molecules separately like this, Rx and Rx. it reacts with the sodium metal, and this NaX like NaCl, NaBr, this separates out. And these two R's of the two molecules of haloalkane, they combine. So RR plus 2NaX. When the two alkyl groups, they will combine, then that product is an alkane. That product is an alkane. So alkane will form here in this case. Example, if R will take as CH3Cl, reacts this with the sodium metal, second molecule of this. This reaction takes place in presence of dry ether. Dry ether is must in this reaction. Then this NaCl comes out, and these two CH3, they combine with each other. CH3 plus NaCl. This alkane is an ethane. But limitation of this reaction is we can only prepare alkanes with even number of carbon atoms by this method. By this method, alkanes with even number of carbon atom can only be prepared. Whenever the two alkyl groups, they combine, we'll get even number of alkyl groups. So that means we are getting alkane here with even number of carbon atoms. This is a limitation of Wood's reaction. So this is the reaction with the metals. With this, the chemical properties of haloalkanes are complete. Now we are moving on to the chemical reactions of haloarenes. Chemical reactions of haloarenes. But before this, we have a question, very important question. Since haloalkanes, we have done that they undergo nucleophilic substitution reactions. Haloarenes, their reactivity towards nucleophilic substitution reactions is very less. So question is why? Why reactivity of haloarenes towards nucleophilic substitution reactions is very less? Now there are a few reasons for this thing. First reason is resonance. I'm taking chlorobenzene here. This has 3 lone pair of electrons with it. Now these electrons are moving towards benzene ring. So the lone pair moves here and this becomes a double bond. When electron comes here, this becomes a double bond. But whenever any atom uses its lone pair, it will get a positive charge. So positive charge will come here. But if we have a double bond here, this carbon will have 5 valency, which is not possible. So when this electron is moving here, at the same time this double bond from here will come out on this carbon as a negative charge. So this will happen in the first step. Now since benzene is electron rich molecule, the electrons which are coming on the carbon here will spread on this entire benzene ring. And how these will spread? This will move here and this double bond will come out here on this carbon as negative charge. So this resonating structure is no change in this part. Now when the electron moving here, a bond will form here. And when this double bond comes out here on this carbon gets a negative charge. Now next, this negative charge comes here. When negative charge comes here, then there is a bond here. So when bond will come here, this carbon will now have 5 bonds, which is not possible. That means when this negative charge moves here and forms a bond, at the same time this bond will move and come out on this carbon as negative charge. And now last resonating structure is this negative charge comes here and this comes back here on this Cl. So as a result of this again will become single bond and the bond is coming out on the Cl. So Cl will again get back its lone pair of electrons. So these are the 5 resonating structures. And this is the 5th one. Now if we see the 2nd, 3rd and the 4th resonating structure, we'll see there's a double bond between carbon and Cl. Between carbon and Cl there's a double bond. Now for the nucleophilic substitution reaction, this bond should break and in place of this a stronger nucleophile should attack. Like this should be replaced by, substituted by some other stronger nucleophile. This should take place in the nucleophilic substitution reaction. Now the breaking of this bond will be difficult due to resonance, because due to resonance this C and Cl gets a partial double bond here, and breaking of double bond is difficult as compared to breaking of a single bond. So the attack of nucleophile will be difficult in haloarenes. So reactivity of haloarenes is very less towards nucleophilic substitution reactions as compared to haloalkanes, in which there is just a single bond. So this is the first reason, that is the resonance. Now second reason is hybridization. In hybridization, if we take haloarene and we take haloalkane, here we have a double bond, so this carbon is sp2 hybridized. Single bonds here, so this carbon is sp3 hybridized. And we know sp2 hybridized carbon atoms are more electronegative. They are more electronegative as compared to sp3 hybridized carbon atom. If this carbon is more electronegative, this carbon will pull the electrons of the C-Cl bond to its side. So when electrons of this bond are going towards carbon, this bond will become short. So it will happen like this. Due to more electronegativity of this carbon, this is more electronegative. So it is pulling the electrons of this carbon Cl bond to its side. So because of this, this bond will become short. So C-Cl bond is short here. It's difficult to break a smaller bond than a longer bond. Since this bond is small, it is difficult to break. That is why reactivity of haloarenes is less in nucleophilic substitution reactions. And the third reason is instability of phenyl cation. Instability of phenyl cation. The phenyl cation formed. How this phenyl cation will form? Because of self-ionization. Itself, when it ionizes, then this Cl is coming out with the electron, so this carbon gets a positive charge. This becomes a phenyl carbocation. So because of self-ionization, there will be a phenyl cation formed, but it will not be stabilized by resonance. Not stabilized by resonance, because there are no electrons for resonance. Instead, there is a positive charge. So if it is not stabilized, that means this is not breaking easily and this is not changing to phenyl carbocation. So because of these reasons, resonance, hybridization and instability of phenyl cation, the reactivity of haloarenes is less as compared to haloalkanes in nucleophilic substitution reactions. So after doing this question, now we are doing the reactions of haloarenes. So their reactions, nucleophilic substitution reaction only, but it will not be easy. The first reaction here is called a Dawes process. Dawes process. In this reaction, like chlorobenzene is reacted with NaOH. So when it is reacted with NaOH, reaction will not take place like this. We have to heat it to 623 Kelvin temperature and 300 atmospheric pressure is required. Then only it will react, and first we will get sodium phenoxide. This ONa will come here in place of Cl. This compound is called sodium phenoxide. And further, when this is reacted with HCl, then this becomes phenol. So H will come here and NaCl moves out, phenol will form here. And this reaction we can write in one step also. Instead of two steps, we can write it in one step also. Like if we want to write it in one step, first condition, that is for first step, the condition is NaOH, 623 Kelvin temperature and 300 atmospheric pressure. We get sodium phenoxide. Then we add HCl. So that we can write here as a second step, we are adding HCl. So both the steps, conditions, if we write together like this, we can write the final product here. That is a phenol. So from chlorobenzene, we can get phenol by doing the reaction with NaOH. These conditions we have to use an HCl. So the reactivity of haloarenes is less because see, it's not easy to do this reaction at room temperature and pressure. We need high temperature and pressure for this reaction. But if in the chlorobenzene or in haloarene, an electron withdrawing group is attached at ortho and at para position only. At ortho position, NO2, that is electron withdrawing group is attached. Then this reaction, NaOH, temperature now we need is just 443 Kelvin and normal pressure. Then also the reaction takes place and Cl is substituted by OH. So by electron withdrawing group, the reaction becomes little easy. Now we are taking two electron withdrawing groups, one at ortho position and second at para position. Now NaOH and temperature now 368 Kelvin, and we can get Cl replaced by OH here. This will be a product. And if we take three nitro groups at both these ortho positions and at para position also, then we just have to add water. There's no need even for NaOH, and little bit warm it, and Cl can be replaced by OH. In place of Cl there will be OH. So by introducing electron withdrawing groups, the reactivity of haloarenes will be little more in nucleophilic substitution reactions. Now after doing nucleophilic substitution reactions, we are doing the second type of reactions shown by haloarenes, and these are called electrophilic substitution reaction. These reactions are called electrophilic substitution reactions. And we know electrophilic substitution reactions are the 5 reactions, that is halogenation, nitration, sulfonation, Friedelcrafts Alkylation and Friedelcrafts acylation. Now here Cl is a deactivating group, and we have done in 11th class deactivating groups are meta-directing, but this is an exception. In spite of its deactivating nature, it is still ortho-para-directing in nature because it shows resonance also. So because of resonance, we know these electrons are moving here. This bond comes out here. Double bond will come here. Positive charge on Cl, and on this carbon there is negative charge. Now this moves here and this bond comes on this carbon. Now next this moves here and this bond comes out here. Negative charge here. Now see, in the resonating structures, second, third and in the fourth resonating structure, there is a negative charge here at ortho position, at para position and at ortho position. That means electrons comparatively are more at ortho and para positions here. And in electrophilic substitution reactions, electrophile has to attack, and electrophile needs electrons. So it will attack which carbon? Ortho and para carbons, because here it will get more electrons. So here the chloro is, or the halides say, are ortho para directing in nature in electrophilic substitution reactions. The first reaction is halogenation reaction. Chlorobenzene, when reacted with halogen chlorine or bromine in presence of anhydrous AlCl3, that is a Lewis acid, then electrophile from here will attack here at ortho position and plus at the para position. So we will get ortho dichlorobenzene and para dichlorobenzene. After halogenation, second reaction is sulfonation. In sulfonation, haloarene is reacted with concentrated sulfuric acid and heated. The sulfonic group will come at ortho plus at the para position. Sulfonic group SO3 H group. Now after sulfonation, next reaction is nitration reaction. In nitration reaction, chlorobenzene is reacted with concentrated HNO3 in presence of concentrated sulfuric acid. Concentrated nitric acid in presence of concentrated sulfuric acid. These two will react and there is formation of an electrophile NO2 which attacks ortho position and plus it attacks the para position. And this product formed is, this is called 1-chloro-2-nitrobenzene. 1-chloro-2-nitrobenzene. After nitration, the fourth reaction in electrophilic substitution is the Friedelcrafts Alkylation reaction. The fourth reaction is Friedelcrafts Alkylation reaction. In this reaction, chlorobenzene is reacted with alkyl halide like CH3Cl in presence of Lewis acid and anhydrous AlCl3. These two react and electrophile CH3 will form, which will come at ortho and plus at the para position. This compound is 1-chloro-2-methyl-benzene. Now last reaction here is Friedelcrafts acylation reaction. Friedelcrafts acylation reaction. Chlorobenzene is reacted with acyl group. Acyl is this RCO group is called acyl group. Name of this compound is ethanoyl chloride, and commonly this is called acetyl chloride. This reaction also takes place in presence of anhydrous AlCl3, that is Lewis acid. So now these two, they react and this formation of an electrophile COCH3. So this COCH3 will attack ortho position and plus this is attacking a para position, COCH3. This compound formed here is known as 4-chloroacetophenone. 4-chloroacetophenone. Actually, this compound is acetophenone. This is acetophenone. And in acetophenone, at fourth position is chloro group. So this is 4-chloroacetophenone. And this is 2-chloroacetophenone. These are the electrophilic substitution reactions of haloarenes. Haloarenes, they undergo electrophilic substitution reactions. So we have covered up nucleophilic substitution and electrophilic substitution reactions of haloarenes. The third type of reactions shown by haloarenes are reactions with metals. Reactions with metals. The first reaction here is Woods-Fittig reaction. Woods-Fittig reaction, like a Woods reaction only. But in this reaction, one molecule is of haloarene, reacts with sodium metal, but another molecule is of the haloalkane. One molecule of haloarene, one molecule of haloalkane, when they are reacted with sodium metal in presence of ether. In presence of ether. Then this NaCl comes out and the benzene ring will link with the this CH3 group, the alkyl group left here. This compound is toluene. When CH3 links to the benzene ring, that compound is known as toluene, and this reaction is called Woods-Fittig reaction. Now the last reaction here is the Fittig reaction. In Fittig reaction, both the molecules are of haloarenes, written like this. One molecule of haloarene, another molecule of haloarene. reacted in presence of ether. So again here this NaCl comes out and the two benzene rings, they link by a bond. They are linking via bond and this formation of NaCl. This compound is called diphenyl or biphenyl. Diphenyl or biphenyl will form in this reaction. So this is about the third type of reactions of haloarenes, that is reactions with metals.